Let's continue our discussion on Earth's climate past or past climate changes on Earth or Earth's history, because it's not just climate that we are worried about, because Earth, the plates, the mountains, everything evolved, oxygen evolved, atmosphere evolved, life evolved, and climate evolved. And you know that life affected climate because we just talked about plants evolving during the Silurian and the Devonian and photosynthesizing like crazy across the planet and taking down too much CO2 and cooling it down and maybe causing a snowball Earth. Maybe because when you do detective work, you may not get all the pieces of evidence. Let's say an accident happened and you are a detective who is sent to figure out what happened. You may not be able to exactly reconstruct what happened, but you have to take all the evidences and make the best judgment of potentially, possibly, maybe what happened. Okay, so we'll look here at sea level and the blue curve. When you look at the figure, you'll know what we mean. So it shows the average sea level compared to its present level for the whole Earth through geologic time, which means global average sea level, which you know is not constant everywhere, but we will come back and talk about this a little bit later. So this global sea level may be affected by, for example, changes in the volume of water in the oceans or the changing shape of the ocean basins. And you already know that ocean basins change shape because the continents are moving, and you know that volume of water can change because the glacier can build up and take water out of the ocean, or glacier can melt and release the water back, and water can warm and expand and so on and so forth. However, relative sea level changes affecting Britain and Ireland may have differed markedly from this global curve, which means global sea level is not like a bathtub that is rising everywhere, as we will see in a podcast later, but because there are winds and because Earth is rotating, it will have some highs and some lows, and that are very local. But the global mean sea level tells you something. If it is going up, that means you are accumulating energy because you are either melting glaciers and putting it into the ocean again, or you are warming and expanding the waters. Okay, so that's something to keep in mind. For example, there are local vertical changes of the land caused by the movement and interaction of the plates that make Earth's crust, which we have looked at and will look at again here, and by the formation and melting of the ice sheets, which we already discussed. We cannot measure sea level in the ancient past directly, and a variety of techniques are used to estimate past sea levels, and we cannot measure how high it was, but we can see how different it was from what it is present. Was it higher than before, or was it lower than before? Okay, so these we call anomalies. So we can estimate anomalies with respect to the present baseline, remember. Okay, so including evidences of erosion by the sea, the fossil reefs approximating to sea level, and so on. And so this is detective work again. Temperatures, we'll see a red curve that shows the average global temperature back to the Cambrian period, which is 542 million years ago. We cannot directly measure past temperatures. Instead, we use evidence preserved in the rocks that record temperatures in a predictable way. We know how that works. One such method uses the proportion of oxygen 18 isotope found in carbonate fossil shells. A high oxygen O18 content is oxygen 18 is called O18 affectionately, and it's associated with cold sea surface temperatures and times of glaciation. So you take a coral or a little zooplankton or phytoplankton that has calcium carbonate shell. You can carefully analyze it in the lab with a mass spectrometer and so on and so forth, and say whether its oxygen 18 is higher than the baseline from the modern times or lower, and we know that that shell got formed at a higher temperature or a lower temperature. Okay, so we'll see some white bars next to the curves that show ice ages when ice covered the polar regions. Note that although the Earth experienced an ice age during the Permian, Britain and Ireland were enjoying tropical conditions. Obviously, climate and weather are very local, but we track global quantities like global temperature and global sea level to see if we are continuing to accumulate energy and so on. So we'll also reconstruct globes to show how the continents have moved across the surface of the Earth through geological time as a result of plate tectonic activity. When the plates or the continents move, we call them plate tectonic activity, variously splitting apart and reassembling everywhere in changing patterns. That's again a nice detective work. How do we know that India was way south of the equator before 100 million years ago? We use magnetic lines and other things to see that it was in a high latitude and now it has moved to a low latitude, because these magnetic lines are stored in the rock. So if you know how old the rock is, which we can do with these chemical evidences, biogeochemical evidences, we can use magnetic lines together to say, hey, India was way to the south before. Okay, so the timeline before 542 million years is not drawn to scale but condensed to fit the poster that we will look at. Time gaps indicate where the rock sequence is incomplete, so the geologists keep on going out there and trying to find the rocks to fill all the gaps. These are the rock stars. Haha. Rock stars, they study rocks to tell us what happened in the past, right? So the rocks have a very nice story to tell about the past history of Earth, its climate and so on. Phases, we look at volcanic eruption and igneous intrusions and mountain building, and the color banding of the timeline indicates the predominant environment or process like this. And typical examples of life forms preserved as fossils in the rocks of Britain and Ireland. Why? Because they are the ones providing us this information. So here is a small map of Britain, UK, United Kingdom, Ireland, and so on and so forth. So they have split it into these pieces. I didn't find a way to cleanly split the brochure, which is a very big file, and you cannot show it all together, so I have to cut it into pieces. So I'm going to do it like this. So we'll ignore the maps for the time being and just follow the text and the figures. Okay, Earth's climate is predicted to change rapidly in ways that could have serious consequences for humanity, which is why we are talking about climate change here. However, climate has varied throughout the billions of Earth's geological history. Rocks record evidence for past climates, including the extreme conditions that have been linked to mass extinctions, like the disappearance of the dinosaurs, which is the best example we can always bring up. The present is the key to the past is a vital principle of geology. We look at what's happening now and we take past evidences and interpret the past with the knowledge about the present, about how geology is working now. So the present is the key to the past. As geological understanding improves, so we are better able to forecast the impact of future change may have on us. The past is the key to the future. Okay, the present is the key to the past, and past is key to the future. Let's read a bit more. Many environments and therefore the rocks formed in them are directly influenced by climate. On this poster, each environment is represented by a particular color. Orange areas on map, for instance, show where the rocks that formed in ancient deserts may now be found on the timeline. Orange represents those geologic periods when the climate was hot and arid in Britain and Ireland. The same color is used to highlight photographs of a present-day desert and examples of ancient desert sandstones. sand gets compressed and metamorphized under pressure and temperature and becomes a sandstone. Similarly, calcium carbonate rocks are formed in the Dover cliffs and so on and so forth. Sea level is changing, continents are moving, and different kinds of rocks are forming and keeping the signatures of temperature and so on and so forth. In other cases, however, rocks are formed by geologic processes regardless of climate. For example, igneous intrusions from under the earth, shown in red here, are formed during episodes of tectonic activity. When plates move and open up or come together, they can force igneous material to come out, hot flowing lava, which is going to produce rocks that have nothing directly to do with climate, independent of the surface conditions that are related to climate. Okay, so we'll come back and read more on the rock stories and the rock stars, and it should be like rock music to your ear. So we'll come back and continue the story in the next podcast then. Kids, see you.